general relativity, step by step. I'm trying to find out what this matrix M is here, and yeah, so what I'm going to do is I'm going to find M. I'm going to choose delta t, delta x, delta y and delta z so that delta s squared equals 0. They can be completely arbitrary, but I'm going to choose that anyway. And so what I know, so that tells me that delta t squared equals delta x squared plus delta y squared plus delta z squared. So I'm just going to choose these values and I'm going to see what happens. In order to do this, in order to find out what this matrix is, I'm going to partition it. Maybe I'll use a different colour. Shall I use blue? Green. I'm going to partition this matrix down there and along there because I've already done quite a lot of work on this. So I'm going to choose, I'm going to go back to black, and I'm going to choose delta t squared equals delta x squared plus delta y squared plus delta z squared equals delta r squared, because I'm going to define r to be the Euclidean distance in space. So I don't need that anymore. Don't need this anymore. Get rid of that. Okay, so where am I up to with this? Well, I know that delta s bar squared is going to be equal to m0, 0 delta t squared. That's that term there. Plus, and then because I've made the matrix symmetric, these three guys here and these three guys here are the same thing. So I can just write delta t times what? It's m0i, let me just write it out, delta xi, and we've got two of those because I've got these guys and these guys, which are the same thing by construction. You'll notice here I'm summing over I. Actually, why not just write it in explicitly? Summing from I equals 1 to 3. I'm quite often using the notation that Roman letters like I and J sum from 1 to 3, and Greek letters sum from 0 to 3, sometimes from 1 to 4. But I and J are summed from 1, 2 and 3. Whereas alpha and beta and gamma are summed 0, 1, 2 and 3. I think I've mentioned that before. Okay, so we've got that, plus these terms here, plus this block of 9 here. So that's going to be summed over I and j, mij, delta xi, delta xj. T squared. Well, that's fantastic. Let me just, oops, said Daisy, these things happen. That's great. What I'm going to do is write it out again. Delta s bar squared, m0, 0, delta t squared, plus, and instead of delta t, I'm going to write delta r times m0i delta xi. Oh, there's a 2 there as well. Plus mij delta xi delta xj, where I and j are summed 1, 2, 3 as it says here. Well, straight away I can do some cancelling. Straight away I can spot that this guy is equal to 0. Why? Because I can change the sign of x and delta y and delta z, and that changes the sign of this, but not the sign of this term here. So that one changes sign, but this one doesn't change sign. So the whole thing must be a 0 here. Yes, what do I do now? Yeah, I've just made the observation that delta r equals, oh, I'm writing in red, that's not good. Let me go back to black. I'm just making the observation that delta t equals delta r. Because I'm on a light path here. So what have I got here? I've got delta s bar squared equals m0, 0, and I'm going to substitute for delta t squared. That's going to be delta x squared plus delta y squared plus delta z squared plus that zero term there, which I'm not even going to write down, mij delta xi delta xj. And that equals 0 for arbitrary values of xi, for arbitrary x1, x2, x3, I guess delta x, delta y and delta z. So it's true for arbitrary values because all I do is choose my value of time accordingly. Okay, well we'll write that down, and that equals 0 for any value at all of x and y and z. The added piece of information comes from the fact that the speed of light is the same for all observers, so that's what I'm using, and I'm coding it up mathematically as by saying delta s squared equals 0. That's how I was able to substitute for delta r here, and that's how I'm able to substitute for no, I'm substituting for delta t there by delta r, and I'm going to substitute for delta t squared here. Okay, so let's just have a look at this. We've got 0 is identically equal to m0, no, let me write it out in a bit more care here. Delta x, delta y, delta z times a matrix. What I'm going to do right here, why is it equal to 0? It's 0 because it's equal to that, and I'm choosing a light beam. And now I'm just going to express it as a quadratic form. So I'm going to have a delta x, a delta y, and a delta z. Yeah. So I've got m0, 0 plus 1. That 1 from here. M row 1, column 2, m row 1, column 3, m... no, it's not a 1, it's an m11, sorry. I'll write this out again a bit more neatly. Plus m11, 1, 2, 1, 3, 2, 1. And of course this is symmetrical anyway. This is m0, 0 plus m2, 2, m row 2, column 3, m3, 1, m3, 2, m0, 0 plus m3, 3. And that identically equals 0 for any values of delta x, delta y, delta z. All I've done is observed that this thing here is a quadratic form with delta x, delta y, delta z multiplied by the identity element, which is here, here, and here. And then this guy's arbitrary, so I've just left the m's in there. Now here's the killer. I know that this must be a 0 matrix. Because the quadratic form with any combination of delta x, delta y, and delta z is equal to 0. This is quite a common line of logic in relativity. So I know that all the entries are equal to 0. So that tells me that the off diagonal elements m12, m13, and m23, I guess, are all equal to 0. So all I've got left here is m00 plus m11 equals 0. Because I know this element on its own is equal to 0. This element on its own is equal to 0. So that tells me m00 plus m22 equals 0. And m00 plus m33 equals 0. Well, that's nice. That tells me that m11, oops, pinch in a little bit. That tells me that m11 equals m22 equals m33 equals minus m00. Whew. Now, what was I doing all this for? Why was I doing all this? What I was doing was trying to find this matrix here, this M matrix here, which gave me an expression for the interval in the alternative coordinate system, the blue coordinate system, which was moving in the spaceship here. So how does the blue guy calculate the interval? The blue guy calculates the interval according to this matrix here, and so far I've done quite a lot of work on this because I've shown that the off-axis elements are all 0. These three guys here were 0 for some reason. Oh yes, because of the swapping sign argument. Those are 0, and these off-diagonal elements are 0 as well. So we've got quite a lot of work here. We've done quite a lot of work here. So what does that tell us? That tells us that the matrix, which was M 000, M12, M13, and all the way down to M33, I can use these relationships here and specify M00, 000, 000, 000, minus M00 from this relationship here, 0, I'm going to space. Let's do this again, it's going to drive me nuts. M00, 0, 0, 0, 0, 0, 0. This term here is M11, and from this line here, I know that's equal to minus M00, 0, 0, 0, 0, M00, 0, 0, 0, 0, minus M00, 0. Whew! So that's my matrix M. So let me remind myself what that's telling me. That's telling me that delta S bar squared equals, and it's an abusive notation which drives me nuts, delta X, delta Y, delta Z, times this beautiful diagonal matrix here, M, oh no, minus M00, minus M00, minus M00, 4x4 matrix, times delta T, delta X, delta Y, delta Z, equals M00 times delta T squared minus delta X squared minus delta Y squared minus delta Z squared, because I've managed to factorize this thing in terms of M00. So what I have to do now have to find M00. And I thought this would be easy, but it's in fact a little bit harder than it might appear. I'm going to do it in the next screencast, so I'm going to stop there. Stop.